In other words, find the n that makes this event most likely. That's called the maximum likelihood estimator. Okay? So we want to find the n that makes this probability the largest, because that's what happened. So the most probable thing is probably what happened, right? So we find the n that maximizes P of A. Okay, so one way to do this, we'll call this f of n. It's a function of n, right? And now, when you're working with binomial coefficients, what do they look like? They're products of numbers like from 1 to n, or from here from 1 to 10, and divide by the product of numbers 1 to 4, and then 1 to 6, etc. They often lead to lots of cancellations if you do the right thing. Because if you get, like, what's n plus 1 factorial divided by n factorial? N plus 1, right? So in here we'll have an n minus 10 factorial and n factorial. If we can get rid of all the stuff except the n and the n minus 10 somehow, that would be nice. So a lot of times what you might do is look at ratio of this to maybe f of n plus 1. So let's look at f of n plus 1 over f of n. So we want to do what? How do we pick n? Suppose this ratio is bigger than 1. If this ratio is bigger than 1, which event is more likely, the one with n plus 1 or the one with n? One with n plus 1, right? So we'd go with n plus 1. But then we'd want to maybe check to see maybe n plus 2 gives a bigger result. So we're going to look to see if f of n plus 2 over f of n plus 1 is bigger than 1. So what we want to look at is, when is this bigger than 1? When it stops being bigger than 1, that'll be our estimator. Okay? When we find an n, so that's bigger than 1, but f of n plus 2 over f of n plus 1 is less than 1, then n plus 1 would be our estimator. Because what does that say? F of n plus 1 is bigger than fn. So that's the event with n plus 1 is the population is more likely. But this one says f of n plus 1 is bigger than f of n plus 2. So things start going down. They are going up until n plus 1, and they're going down after n plus 1 if this happens. Okay. So let's look at this ratio. We should expect miracles. Well, okay, in the numerator, this will occur in both f of n and f of n plus 1. So when I divide one by the other, the 10 choose 4 will cancel. So I'm not going to write down the 10 choose 4. So this ratio, so it'd be what? N minus 9 over 16 divided by n plus 1 over choose 20. Okay? That's with the n plus 1. Why n minus 9? Right. Right. And then we divide by what we get when you have n in there. And that would just be, when you divide by a fraction, you invert and multiply, right? So I get n choose 20 in the numerator here. And down here I'd get n minus 10 choose 16. And now we're really in business, because if we write out the expressions here, this becomes that term. This one is that term. Down here we get, let me write it over here. This term, that's from here. And then this one I'll put here. Okay, so this and this cancel. This and this cancel. Now let me maybe invert and multiply. So I get n minus 9 factorial, n factorial. This goes in the numerator, n minus 26 factorial. This goes in the numerator, n minus 19 factorial. And then in the denominator we have n minus 25 factorial. I'll put that here. That's from here. N minus 10 factorial, I'll put that here. N plus 1 factorial, I'll put that here. And then n minus 20 factorial. Okay? And what happens now? This ratio leaves what? N minus 9 in the numerator. Okay, so we've taken care of this part. What about this ratio? So n plus 1 in the denominator. This ratio, n minus 25 in the denominator. And this ratio, n minus 19 in the numerator. Okay, that's our ratio then. Not bad. Okay, so what did we want to do? We want to check when is this ratio bigger than 1? Okay, we want to find the last n plus 1 for which this is bigger than 1. Or we pick the first n for which that is less than 1. Well, I mean, after it gets. So let's check. When is that bigger than 1? It's bigger than 1 when n minus 9 times n minus 19 is bigger than n plus 1 times n minus 25. Right? That ratio is bigger than 1 if the numerator is bigger than the denominator. Let's multiply out both sides. Get n squared minus 28n plus 9 times 19. And 71. Okay. The n squareds cancel. Let me subtract 25. I'll subtract n squared from both sides. Subtract 25 from both sides. 25 from this gives 146. Is that right? Oh, okay. I'll add. 196 is bigger than 4n, or n is less than 4 into this goes what? 40 what? 49 times. Okay? So as long as n is less than this, ln plus 1, fn plus 1 over fn is bigger than 1. After that, it's less. So what integer n, what's the biggest integer n that's less than 49? 48. So what's our estimate? N, not n, but n plus 1. So 49 is our estimate. So the estimated population size would be 49. Okay? The largest n that's less than 49 would be 48. But we want to take n plus 1 because the probability with n plus 1 is bigger than the probability with this n. Okay, so that would be 49. After 49, the probability starts going down. So 49 is the population estimate. This is actually used as kind of okay, well, if binomial is good, multinomial is even better, right? And what's the multinomial theorem? Question, how many ways are there to do this? So maybe think of the closets as being boxes or something. Okay, so we want to put n1 objects in here, n2 objects in here, n3 in here, etc., and r in there. Does everybody understand? Okay, so we just use the multiplication principle. Let's count how many ways there are to put n1 things in here first. And then for every one of those ways, we count how many ways there are to put n2 in here, and we multiply them together. And for every one of the ways we've done that and that, we count how many ways there are to do this, and just keep it going. Okay, just use the multiplication principle. So how many ways are there to put n1 objects in here? We have to select, do what? Select n1 objects from n. So that would be n choose n1, right? And now, how many, given any one of those choices, how many ways are there to put n2 objects in here? Right, n minus n1 choose n2. And now once we've done those two jobs, how many ways are there to do this one? You guys are good. And then down to here, we get to n minus n1 minus n sub minus 1, choose n sub r. But actually, what would this number be? How many objects are left after we've done all the other jobs? N objects, so we have, this is 1. Because what's this number after all? If I subtract the first n r minus 1 of these, well, if I subtract the first r minus 1 from here, what do I get? N sub r. N minus the first r minus 1 would be n sub r. Okay? So that last number is 1. Okay, so that's pretty long, complicated looking expression. Would you like to compute it that way? Or you'd probably want to simplify it first, right? Because you all have the same instinct as a mathematician does. A mathematician always wants to make things simple. Do you believe that? The goal of mathematics is to make the description of the world simpler. So let's simplify. And like many expressions involving multiplying and dividing factorials, this admits a big simplification. Let's write these out. This is n factorial over n minus n1 factorial times n1 factorial, right? This would be n minus n1 factorial times n minus n1 minus n2 factorial times n2 factorial. The next one is n minus n1 minus n2 factorial times n minus n1 minus n2 minus n3 factorial times n3 factorial, etc. All the way down to, well, 1. And look at this. It's like falling dominoes. That cancels that. That cancels that. This one cancels the next one. So what will be left? Well, in the numerator, what survives? In the denominator, n1 factorial, n2 factorial, n3 factorial, all the way down to n sub r factorial. Okay? That's called the multinomial coefficient. The multinomial theorem says that x1 plus x2 plus dot 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 plus xr to the n is a sum over oh, and by the way, we use this symbol here. And say n choose n1, n2, n3 through nr. Okay. So we sum over all sets of non-negative integers, n sub I, that add up to n, this expression. That's just like the binomial theorem, only more. And same argument. Okay, so where would the multinomial theorem ever come up? Well, who wants to come over Saturday night to my house to play poker? Anybody? 1? Any more? 2? 3? 4? 5? Okay, that's enough. So, 5 of you said you'll come and I'll play. So that's how many? 6. And so we're going to play 5-card poker. I mean, any poker game you wish with 5 cards. So I'm going to deal from a deck of 52. I'm going to deal out 6 hands, 5 cards each. And before you can bet, I'm going to ask you how many ways are to do that? How many ways are there to deal 6 hands with 5 cards each from a deck of 52? That's one of these problems. Instead of boxes or closets, I'm going to deal to 6 people, 5 cards each. So how many ways are there to do that? Well, what's the little n? What's the total number of objects I have? I have 6 players. Am I going to deal out all the cards? No. I'm going to put 5 cards in here, 5 here, 5 here, 5 here, 5 here, 5 here. What else do? I put the other rest of them on the table, and we use those for drawing, right? So I'm going to have a 7th box here where the remainder go. So I'm going to put 5 cards here, 5 cards here, 5, 5, 5, 5, and then how many? 22. So the number of ways to deal 6 poker hands would be 52, choose 5, 5, 5, 5, 5, 5. I should have done this with something that had 9s because of the Beatles song, number 9, number 9. And then 32. Right? That's the stack that remains after doing. Okay? 1, 2, 3, 4, 5, 6. So it would be, oh, sometimes I do that to see if you're watching. 52 factorial over what? 5 factorial to the 6th, and then 22 factorial. Okay? Another example would be playing bridge. By the way, I'm busy Saturday. I can't have you all over. Sorry. I just remembered that. What about bridge? Anybody here play bridge? You play with a deck of 52? Nobody plays bridge? No? Well, do you know how many cards each player gets? Do you know how many players there are? No. Does anybody know how many players there are in a bridge game? Right, 4. And how big is the deck? And they all get the same number, so they each get 13. So the number of possible bridge hands would be that's an enormous, enormous number. So just one last little question. If you're tossing a coin, how long do you expect to toss until you get a head if it's a fair coin? How many tosses do you think you should expect to have to make before you get a head? On average. Well, the answer is 2. If you're rolling a die, how long on average do you think you have, how many times do you think you have to roll it before you get a 1? 6 times, yeah, 6 times. So in bridge, how long do you have to wait until you get a particular hand? Say where the first person gets all spades, the second one gets all hearts, the third one gets all diamonds, and then the last one gets all clubs. It would be 1 over this number. That'd be the average time until that happens. Turns out the universe isn't that old. I mean, you know, it takes some time to deal out a hand. Or at least the Earth isn't old enough for that to have happened. Yet, I remember years ago watching TV, and a group of elderly women came on and said that that happened when they were playing. I'm suspicious. Okay, so let's take a break, and we'll come back a couple minutes after 10. Okay, it's time to talk about conditional probability and independence. the most fundamental notions in probability theory. You have two events. And the probability of one of them is positive. Then the probability of A given B is denoted by this expression. We read probability of A given B, and it's equal to probability of A intersect B over probability of B. So let's do a simple example. What's the probability you get a 6, given that the outcome of the roll was an even number? Any guesses? Yeah, 1/3. Why 1/3? Right, and is there any reason for one being more likely than the other? No, so this is one of these examples of a probability where all outcomes are equally likely. There's really no bias among the even numbers or among the odd numbers. There's no reason to suspect there is. So the answer should be 1/3 here. Can we get that from here? Probability of A intersect B? Well, A is a subset of B, is it not? Or, they say in England, isn't it? So this would just be probability of A divided by probability of B. And what's the probability of A if the die is fair? 1/6. And the probability of an even number? Well, this is one of those problems with a probability space with equally likely outcomes. So all we have to do to compute the probability of B is count how many ways there are for that to happen divided by the total number of outcomes. How many possible outcomes are there when you roll a die? 6. How many ways are there for B to occur? 3. So this is 1/2. And 1/6 divided by half is 1/3. Another way to write this is the probability of A intersect B is the probability of A given B times the probability of B. And again, totally trivial formula, but sometimes you might want to compute this, and it's not completely obvious what the answer is, but this side becomes simpler. Computing probability of A given B sometimes might be easier than probability A intersect B. And then if this is also simple to compute, you could just multiply the two simple answers together to get the more complicated one. So Another useful tool for computing probabilities is the following. V1 through Vn are mutually disjoint events. Their union is the whole sample space, and each has a positive probability. Then probability of A can be computed using these. That's called the law of total probability. And to see why this is true, the thing I've underlined is this side, right? With a BI instead of a B, as you see here. That would be this, right? Probability of A intersect BI. What about the sets A intersect BI? Are they mutually disjoint? So maybe let me take one moment then. This side over here is also this, right? And this is equal to this. Why is that? That's the definition of a probability. These are disjoint sets. If I intersect A with BI, if the BI's are disjoint, then their intersection with A is also disjoint. And the probability of a union of disjoint sets is the sum of the probabilities of those sets. That was in the definition of probability. And then this could be rewritten A intersect that union This is something called De Morgan's laws. There are a bunch of rules for how unions, intersections interact. This is what would happen here. And what's this set here? The union of the BIs. It's all of omega. So what's A intersect omega? Just A, probability of A. Okay. So it's very simple to see why that's true. Let's try to use it. Erden problems are very popular in probability theory and math physics. They are used in models of statistical mechanics. Here's an Erden problem. Nice urn here. A bunch of balls inside. White ones. And green ones. Okay. You can think of these if you want, if it would make you more attentive. The white ones are peppermint gumballs, and the green ones are spearmint gumballs. You can reach in and have one. But you have to return one of the same, return that one and two more of the same color. ball is drawn at random. I'll call it a gumball. Its color is noted. And replaced. Together with two more of the same color. Then the selection is repeated. And is after the ball's been put back in, you draw one more out. Second draw is made. If G2 is the event, the second gumball is green. What is the probability of G2? Is it obvious what the probability is? There are 5 green balls and 8 white balls to begin with. I take it nobody knows the answer right away. You know the answer? Oh, okay. Pardon? Yeah, it's easier if we know what happened the first time, isn't it? That means we should condition on what happened the first time. We should use this law of total probability where the B's are what? Indicate what happens. They should exhaust all the possible outcomes from the first draw. What could happen first draw? Green is drawn or white is drawn. So our sets here, B, should be maybe what would be good choices for describing green is drawn the first time? What would be a good way to denote the event? Green is drawn the first time. What, yeah, G1, and how would you denote white is drawn the first time? W1, okay? So naturally, we take G1 as the event white is drawn first time. And W1, whoops, just kidding. Green is drawn first time, W1 is white is drawn first time. And then, of course, G1 union W1 exhausts all the possibilities. Even if we keep drawing, either we have to have white the first time or green the first time. Okay? And what about the intersection of these two things? It's empty because the ball can't be simultaneously white and green. And what about the probabilities? Are they positive? What's the probability of G1? Right, because this is one of those examples of a probability space where all outcomes are equally likely. So you just have to count the total number of possible draws for the first time. How many different possibilities are there when you're trying one thing out of 13? 13, choose one, or 13, right? And how many ways are there to get a green one? 5 ways. So 5 out of 13. And probably of W1 is, again, well, 8 over 13, right? So they're both positive. So we can apply the law of total probabilities here with B1 equal to G1, B2 equal to W1. Okay? So, and N is 2 in our case, right? So the probability of green the second time would be, well, there are two sum N's, so I'm not going to use the summation notation. It would be probability of green the second time given green the first time times probability of green the first time plus probability of green the second time given white was drawn the first time times the probability that white is drawn the first time. Now, are these probabilities easy to compute? We already did these two. What about probability of green the second time given green the first time? What would that equal? Yeah, because what's the urn look like after green is drawn the first time? We replace that green ball and put 2 more in. So now how many green balls would be here? 7. And how many balls altogether? How many? I replaced the one I did draw, and then I put 2 more in. So 15, right? So that conditional probability is 7 out of 15. And then times probability of green is 5 out of 13. What about this conditional probability? What does the urn look like on the second draw if white was drawn the first time? How many green balls are there now? 5 still, and altogether there'd be 15. So the probability of green the second time, if we had white the first time, would be 5 over 15. And then times, what was this? 8 over 13. Question? Here? This one. Okay. So remember, we're putting the ball we selected back and 2 more. And so we started with 13 and we add 2 more, so that now at the second draw there are 15 balls. Okay. Any other questions? All right. So let's repeat it again. What's probably the third one is green. Is this easy to do right off? I mean, just by inspection? No, I think it requires some analysis, a little bit. Okay. This is easier to do if we know what we're drawing from, right? It would be easier to know what the probability of getting green the third time is if we know what the urn looks like on the third draw. Right. Thanks. So let me update this. So if we knew the composition of the urn after 2 draws, computing this probability would be easy. It would be the number of green balls over the number of balls. How many balls will be in the urn for the third draw? 17, right? So last time we conditioned on what happened on the first draw. This time we should condition on what happened on the first 2 draws, right? We should condition on what happened on the first 2 draws. So what could happen on the first 2 draws? We need this G1 and W1. We also need G2 and W2, which will have natural meanings that I don't have to write down. So what are the possible things that could happen the first 2 times? The 4 possibilities are there 4 possibilities? Okay, thank you. G1 intersect G2. That would be our B1. G1 intersect W2. That would be something like B2. W1 intersected with G2, and then W1 intersected with W2. Those are the four possibilities for the outcomes of the first two draws. White, then green, then green, green, then white, white, then green, white, then white. These are mutually disjoint, correct? Their union is all possibilities, right? The union of these would be omega. Is each probability positive? Yes. So we can use the law of total probability. And we would get probability of G3 would be probability of G3 given G2. Let me write it this way. G2 time and G1, if I write consecutively, this means intersection. So it's like a contraction. Times the probability of G2, G1. So let me abbreviate, etc. Okay, now I can easily compute the conditional probabilities. What's this conditional probability? All you have to do is ask yourself how many green balls are in the urn now. First time I added 2 more. Next time I added 2 more. I started with 5, so now I'll have 9 in an urn with 17. The chance of getting a green would be 9 out of 17. And now this one I'm going to write as probability of G2 given G1 times probability of G1. Just use the definition of conditional probabilities. That was one of the formulas I wrote earlier, right? Probability of an intersection is probability one given the other times the probability of the other. Why do I do that? Is this easy to compute? Yes. Is this one easy to compute? Yes, it is, because I know what's in the urn if I condition on what happened the first time. So any question on this? This is just using the probability of this intersected with that is probably this given that times probability of that. This probability? Yeah, because now there are only 2 additional greens have been put back in. There are 17 balls altogether, so this would be 7 over 17 times probability of G1 given, I'm sorry, W2 given G1 times the probability of G1 plus what's this probability? G3 given W1 G2. Well, here 2 green balls have been put in. So it'd be 7 over 17 again, right? And then times the probability of G2 given W1 times the probability of W1. Plus here we get what? No more green balls are in, so there's still 5 in an urn of 17. Probably getting a green then would be 5 over 17. And then probability of W2 given W1 times probability of W1. And now I think we can fill out the rest. We get 9 over 17. What's this probability? There are 15 balls in the urn on the second draw, right? And 7 green, so 7 over 15, and this would be 5 over 13, plus 7 over 17 times Well, how many whites are there? Same as there ever was. 8 over 15 times the probability of getting green the first time. That's 5 over 13. There, we get 7 over 17. Here, 5 over 15. Is that right? Because there are no additional green balls, but there are 15 in the second draw. And here would be 8 over 13 plus 5 over 17. Here we get 10 over 15. And here we get 8 over 13. Okay, so somewhat difficult problem becomes a series of, or somewhat difficult computation, probably green the third time, becomes a series of very simple ones. Another important and useful formula when doing conditional probabilities is called Bayes' rule. Under the same conditions as the law of total probability, so if we take A to be something like G2 and B1 to be W1, B2 to be G1, then B1 and B2 are disjoint. They have positive probabilities. Their union is the whole sample space. And we might ask, what's the probability you had white the first time, given you got green the second? It's a little backward, isn't it? It's kind of like, this is a problem where if you could just reverse those, it'd be easy to compute, right? Here's a little difficult. It's sort of like, this is the effect and that's the cause. And now we're asking what was the possible effect or cause given the effect? Which reminds me of a story I heard on the radio as I was driving somewhere. Seems like I'm driving all the time, delivering kids activities. It said, the report said that children of working mothers were more likely to be obese. Children of working mothers were more likely to be obese. And I was wondering, what is it about obese kids that makes their moms want to go out to work? So it's right. So it's it's obvious that people think the effect is the other way. So we might compute conditional probabilities in this order. Now this is what Bayes' rule does. It kind of reverses the way the conditioning is going. Puts it kind of in an order that's easier to compute. So this would be the probability of what? G2 given W1 times the probability of W1 over, well, we just have a sum of two things, so I'm not going to write the summation notation. It would be probability of G2 given W1 times probability of W1 plus the probability of G2 given G1 times probability of G1. Okay, that's the application of Bayes' rule. Now these are more natural and easier to compute directly, just like we've been doing. And what do we get in the numerator? Well, if white was drawn the first time, there are now 10 white balls, and they're earned with 15. Probably getting a green would be 5 out of 15. And the probability of getting white the first time was 8 out of 13. This term goes here. And then here, probably getting green the second time would be 7 out of 15. And then probably green the first time was 5 out of 13. And you could simplify that. Okay? So this problem was a little bit confounding, became a bunch of simpler ones using Bayes' rule. So whenever you come across a conditional probability that looks like it'd be easier to solve if the conditioning was and the event were reversed, then use Bayes' rule. Okay. If probability of B happens to be positive, then independence is equivalent to the probability of A given B is probability of B. I'm sorry, A. What does this say? If you know that B happened, what's your estimate of the chance that A has happened? Does information about the occurrence of B tell you anything about the probability or likelihood of A happening? It tells you nothing, gives you no information. So let's think of some examples. Suppose I toss a coin twice. Comes up. I tell you it comes up heads the first time. What's the probability it comes up heads the second time? Is it changed? Why not? What would have to happen in order for the probability to change? Something about the first toss would have to affect the second one. Does the coin remember what it did the first time? You better say no. No, there's no memory. The coin has no recollection of the first event, and even if it did, could it do anything to control the outcome of the second event? No, not likely. Or it's not something we consider possible. Let's actually consider the sample space of two coin tosses. Okay, so how many possible outcomes are there when you toss a coin twice? And they're equally likely, right? So let's try to see if that or that holds, where A is the event heads the first toss, and B is the event heads the second toss. Well, maybe I should do this the other way around. Sorry. Let's compute the probability of A intersect B. That's what? Heads, heads. That's 1 out of 4 equally likely possibilities, so the probability of that is 1/4, right? What's the probability of A? Maybe I should call, yeah. Let me do two more events. C is tail on the first toss, and D is, well, that'll be enough. That's all I need. Okay. A can be decomposed as probability of A intersect B plus probability of A intersect C. Right? Heads of second toss is the union of heads the second toss and heads the first toss together with heads the second toss, tails the first toss, right? And the reason I do that is now this is in our sample space. This is 1 of 4 equally likely outcomes, namely heads, heads. This is 1 of 4 equally likely outcomes, namely tails, heads. Each of these has what probability? 1/4, so that would be 1/2. And what about the probability of B? Well, our sample space is 2 tosses. I don't think I have to go through it. What's the probability of heads the first time? 1/2. Okay. So what's the probability of A times probability of B? 1/4, right? And that happens to be also the probability of A intersect B. So the outcome on consecutive tosses of a coin would be independent, as if you toss it twice. What if you toss it 3 times? All we use here was this equally likely property. So any 2 tosses would be independent. What about rolls of a die? We do the same computations, but instead of 1/2, we get 1/6, right? And if you roll the die twice, each outcome would have probability 1/36, and 1/6 times 1/6 would be 1/36. So consecutive rolls of a die would be independent, or if you roll die 10 times, the first roll and the 10th roll would be independent by similar computations. What about in the earn problem? What about G2 and G1? Are they independent? What was the probability of G2? Did we compute that? Or in here, what about probability of G2 given G1? Is that the same as the probability of G2? Which is bigger? This one's bigger, right? The answer here is no. So what happened here? The outcome does the outcome of the first draw affect the outcome of the second one? Very much, right? So there's no independence here. So if there's some sort of memory or mechanism for carrying over information from the past to the present, then you probably won't have independence. But if there is no such mechanism, then you should have independence. Okay, so maybe you throw the dart 70 times. Each time you have probably 0.05 of hitting the bullseye. And each trial is independent of the other trials. Let's assume that. What's the probability you get at least one bullseye? Now, on Monday, I told you that sometimes you might want to compute the probability of A. But it's easier to compute the probability of A complement. A looks a little bit complicated. There are probably a lot of ways for you to get at least one bullseye. It could be the first time, the 20th time, second and the 18th, and the 35th time. Sounds like a pretty complicated counting argument. How many ways are there to never get a bullseye? One way, every time you miss. So if this is, there's at least one, this would be that there are none. This, I think, should be easy to compute. What's the probability there are? Let's think about something like even simpler, tossing a coin. What's the probability you don't get ahead the first time? What's the probability you don't get ahead the first two times? A fourth, because the trials are independent, right? And each one has probability of half, and the probability of each one, probably both happening, would be the product of the probabilities. What about not getting ahead if you roll it 3 times? 1/8. By independence, it'd be 1/2 times 1/2 times 1/2. The probability of the intersection of those 3 events, heads the first time, intersect heads the second time, intersect heads the third time, would be the product of their probabilities. What's probably not getting ahead 4 times? 1 over 16, 5, 1 over 32. So it'd be 1/2 to the n if you're looking at the probability of not getting ahead n times 0. Now let's go to a die. What's the probability of not getting 1 first time? 1/6. Probably not getting a 1 the first 2 times. 1/6 squared. First 3 times. 1/6 to the third. N times 1/6 to the nth. Now let's say we have an experiment where there's success or failure. Okay. So probability P of success. What's the probability of not succeeding the first time? 1 minus P. What's the probability of not succeeding 2 times in a row? 1 minus P squared. 3 times in a row. 1 minus P cubed. N times in a row. 1 minus P to the n. Success here would be hitting a bullseye, right? Probability of success is 0.05. Probability of failure is 0.95. So what's the probability of failure n times in a row here? 0.95 to the n. This is the probability of failing n times in a row. So it would be 1 minus 0.95 to the n. Okay. And what happens to that as n goes to infinity? Goes to 0. So if you're persistent, eventually you'll get a bullseye. Or consider this. A monkey is randomly typing letters as an infinite scroll of paper, infinite ribbon. Well, this is an old joke. Monkey has a computer and a nice word processor, and he's tapping the keys. And he's been doing this ever since the universe started. There's some chance that starting with one letter, he will type out all the works of Shakespeare perfectly, right? If he keeps going. I mean, there's some given maybe first work of Shakespeare starts with the letter A and is capitalized, and he gets all the punctuation correct. There's some chance that he could do that, but it's pretty small, right? But if he keeps doing it, eventually he'll write all the works of Shakespeare. Okay. Because the probability of failing each time is something like this, and the probability of failing forever will be going to 0. All right, so see you Friday.